All right, hello everybody and welcome to this afternoon session. Let me, you all know the title of the session. I don't have it in front of me, but we're talking about population responses to disasters, environmental events, and policies. And so I want to just say a little bit about how this panel came together. We are, many of us on the panel are part of a working group at the Socio-Environmental Synthesis Center in Maryland. And so we've been working on sea level rise and migration for about a year and a half and trying to really do interdisciplinary work on this topic, which is really challenging. So what you're going to see today is a group of people who are all thinking about these sort of environmental changes and policy and population responses. But because this is such an interesting and diverse group of people attending this conference, I thought it might be useful to just find out who's in the room before we launch into all the presentations. So earlier today, one of the moderators asked everybody in the room who, well, I'm gonna modify what she did. So everybody in the room who works on population, raise your hand. Okay, we got some population people. Everybody who works on sea level rise or environmental change, raise your hand. All right, so we've got a nice mix. Anybody in the room who doesn't work on either of those topics? No. Okay, so I'm
a climate scientist.
Okay.
Does that classify under environmental change? Maybe.
I would say so. And then, how many of us are academics? Okay, many academics. And of those of you who aren't academics, could you raise your hand? Okay, could you just say where you're coming from? Do you work in a university? So I'm just going to call on a few of you. Could you say where you work? You're a journalist, okay. And you?
I'm a science fiction writer.
Excellent. We need more of that. What about you?
I work at Columbia and with NOAA.
Okay. Anybody else want to volunteer where they're coming from? Suzanne?
I'm at Columbia as a teacher of baptism.
Okay. So anyway, it seems like we do have a very scholarly group of people here, as well as some science fiction and non-fiction writers. So that's good to know, just so that we know what we're talking, or who we're with in this room. So let me just say, David Wrathall, who's our first presenter, could not be here today. One of the things that ended up happening with the organization of this panel is that we really shrunk our carbon footprint. Several of the people who were meant to fly in could not make it. And so David didn't fly in, and he was coming from Oregon. So I'm going to give his presentation for him. He's one of the members of this Socio-Environmental Synthesis Center research group. So the paper that we're presenting is not entirely unfamiliar to me, so I will be able to field some questions from it too. I think what we'll do is we'll give the presentations and then just have a longer Q&A at the end. All right, so I'm David. Actually, hold on, I pulled up the wrong notes. Here we go. So over the coming century and beyond, climate change impacts like sea level rise will spatially redistribute the human population. Sea level rise, sea level extremes, and an associated set of environmental hazards like nuisance flooding, inundation, soil salinization, coastal erosion, and land loss will affect where people can live and earn a living. These impacts of sea level change represent an important problem. At the margins, the Earth can become a little bit less habitable, and in those places, people may migrate. What do we know about the numbers of future migrants from sea level change? What are their most likely destinations? What do we know about the timing and sequence of their migrations, especially as sea level change affects different regions in different future decades and then accelerates through the 21st century and beyond. We've tended to frame these questions in the very old, outdated paradigm of environmental determinism, the set of theories that suggest that the environment is a primary factor in shaping the differences that we see across humanity, differences in the human body, in our cultures, and in our behavior. Environmental determinism also drives us to think that environmental change is a predominating driver of outcomes, above other factors like the long-term political context. This ideology is behind the notion that when humans are administered a dose of environmental change, we will see broad, generalizable responses. Too often we take these ideas with us when we consider sea level change and migration. You're looking at a map of regions submerged by sea level rise resulting from emissions associated with RCP 8.5, the business as usual greenhouse gas emissions scenario. This is through the year 2100. These are the areas that would eventually be inundated over time simply from our emissions in the 21st century. Each country shown would have at least 50 million people living in these areas, and each yellow circle represents a city of 10 million that is inundated. Environmental determinism would tell us that these populations were uniformly dosed with exposure to sea level change, and they would respond by moving in generalizable, predictable ways. However, the study of migration clearly shows us that often the key determinant of migration is the policy context. Policies determine where we live, where we make a living, how we make a living, and the options that are available if environmental change undermines our plans. Migration can be extremely responsive to long-term development policies, such as export-led growth policies and industrialization, as well as short-term macroeconomic interventions on interest rates and labor and employment issues. So here you're looking at a map of an imaginary coastline representing the diversity of migration types that might simultaneously occur from hazards associated with sea level change. The dots represent fictional settlements, and the arrows represent migration flows. The reason for considering all of these migration types together is to examine how different policy interventions can be a determining factor for questions about how many people will migrate or where and when they migrate. What is absolutely critical is that migration will likely be responsive to adaptation interventions. Policies meant to address the hazards related to sea level rise, such as nuisance flooding, inundation, soil salinization, coastal erosion, and land loss. Sorry, I didn't say that sentence right. What is absolutely critical is that migration will be responsive to the adaptation interventions. And those are policies that are meant to address the hazards related to sea level rise. These interventions will determine how long it is safe to stay, how long livelihoods will remain productive, who will migrate, when they migrate, and where. If we don't implement policies to adapt to sea level rise, then we may hasten migration. On the other hand, if we do implement coastal adaptations, such as armoring or coastal fortification, we may simply shift migration into the future when hazards eventually overwhelm efforts to adapt. So in this discussion, we've just glossed right over a lot of topics about what kind of migrations might emerge. So if you're interested in a more detailed interpretation of that map, then you can let me know and we can share the paper. To conclude, the key dimensions of future migration from sea level change will largely be dependent on global policy decisions that determine greenhouse gas emissions and local policies that influence where and how we live. Looking forward, a key priority is modeling these policy, migration, sea level rise interactions. In our project, at SYSYNC, we are attempting this, and Reid Bell may speak in greater detail on this topic. Modeling existing and likely policies is important because it will help us identify the policy strategies that can best reduce the adverse consequences of sea level rise to migrants. Like other migrant populations, migrants from sea level rise will have special needs. Wherever they migrate, they will need housing, jobs, schools, healthcare in their new communities. Because policy largely determines how migration occurs, these are problems that we can examine and manage. In this way, sea level change isn't just a problem for Manhattan and Long Island, but also for Chicago, Denver, and Atlanta, all places where people may go, if we're just talking about the United States. So, thank you very much. That concludes David Wrathall's talk. And, sorry, I didn't skip all the way through the different types of, these are all the different types of migration that he was referring to. And here's the list of all of the participants in our SYSYNC working group. All right, so the next presentation is my own. So I'm doing a personality change back to myself. Although on the program, this is scheduled to be presented by my colleague Sara Curran, who also couldn't make it, saving us a little bit more carbon emission by not flying from Washington. All right, so I'll just introduce myself. I'm Beth Fussell. I'm at Brown University. My co-authors on this paper are all at the University of Washington. They're both in the Center for Studies in Demography and Ecology, a population research center, as well as the School of Oceanography. In our project, we consider how climate extremes may affect population distribution across space in the future, but to do so, we kind of think about the past. So our research focuses on the historical record in the United States to look at how climate extremes have affected population distribution. Many case studies exist that provide us with lessons about the interaction between population and the environment. But these case studies tend to focus on the most extreme events. For example, we've heard about, in some of the sessions today, we've heard about Hurricane Katrina in New Orleans. We've heard about Superstorm Sandy in New York and New Jersey. We've heard about Hurricane Maria in Puerto Rico. There are other events that represent sort of more extreme tornadoes and wildfires and floods. And these case studies accumulate and teach us a lot about those specific events, but the challenge is to figure out what is generalizable about those events. So in our project, we sought to learn about the average effects of the full range of hazard events, not just the most extreme events. Here in this study, we used the wealth of population and weather data that's available in the United States at the county level to evaluate our research questions. Our research question is whether, on average, there is a population change response to weather events and property losses associated with them. And if there is, which U.S. counties experience those changes? Hazard-related losses are very geographically specific. Here we can see in the upper right-hand corner in green the combined losses related to hazards in general in the United States for a single year, 2014, And then we can look at all of the specific kinds of hazards and where they occur throughout the United States. It's obvious that hurricanes have a different sort of imprint on the U.S. population than droughts or tornadoes or hail or floods. So while every county experiences some degree of hazard-related losses, different types of hazards concentrate in different counties. Similarly, population growth and decline varies across the United States. The counties in the red scale experienced growth throughout the period of study, which is 1970 through 2009, and you can see that the counties that have grown the most tend to be in the west, as well as along the coast in the east, and then in some other counties in the Midwest as well. The counties in the green scale experienced population decline, and those are mostly counties in the rural Midwest and northern parts of the U.S. But if you were to imagine combining this table or this figure with the hazards figure, it would be hard to see any sort of spatial relationship between hazards and population change. So in this project, we have assembled a data set that basically is the data that you just saw. For every year between 1970 and 2014. These data come from the U.S. Census Bureau, as well as from the Spatial Hazard Events and Losses Database for the United States, also known as SHELDAS, which is currently based at Arizona State University. We use these data to predict the observed population growth rate for each U.S. county in the 3 years following a single focal year. So we look at all years between 1980 and 2009 to predict what the population growth would look like in the next 3 years. We use a modeling technique that controls for other unobserved effects. But to better detect these relationships, we subset our data into 4 different types of counties. And so those 4 different types of counties are described there. We look at counties with the declining population and low population density, counties with declining population and high population density, counties with inclining population, meaning growing population and low population density, and then counties with inclining population and high population density. The reason why we subset them this way is because the majority of counties in the U.S. are actually low density counties, and so if we were to model these all together, the effects would be overwhelmed by those kinds of counties, and so that's why we subset them and look at each of these 4 types of counties separately. So our outcome variable is population growth in the next 3 years, and then we use population growth in the past decade and population density, hazard events and related losses in the current year, and the cumulative number of hazard events and cumulative losses from hazard events in the past decade to look at, to predict future growth. So what are our main takeaways? I'm not going to talk more about the technical details. So the main predictor of future growth in all counties, in all of these 4 subsets, is past growth. And so that makes a lot of sense. There's a path dependency, and what has caused counties to grow in the past is likely to persist and to continue to be related to future growth. But what you see here in this chart is that the relationship is different for each of these different types of counties. So let me just explain this figure a little bit. Each county subset has 3 bars under it that correspond to predicted growth if past growth were at the mean minus 1 standard deviation, at the actual mean, or at the mean plus 1 standard deviation. Okay, so we alter the conditions, And we see that in counties with declining populations, the having a lower than average population growth in the past decade means you'll have slightly higher than average growth in the next 3 years. Having average growth in the past decade means that you'll have slightly lower future growth, and having above average growth means you'll have slightly lower future growth. That's the case for declining counties, and it represents a kind of statistical phenomenon that is sort of well understood, which is regression to the mean, where these counties, what we can really say is that these are counties that have very low and fluctuating growth rates. In the growing counties, we see a different pattern, where below average growth in the past decade is associated with below average growth in the future 3 years. Above average, or average growth in the past decade is associated with slightly higher positive growth in the future 3 years. And then above average growth in the past decade is associated with the highest growth rates. This also makes sense. In these growing counties, the past record of growth is related to higher future growth. And that is perfectly consistent with a century-long trend of urbanization in the United States. It's a very long-standing and powerful trend that is, what we can see here is that it kind of overwhelms every other, or all of the other variables in the model, which have to do with weather and hazard-related losses. So it's not a surprise that there are things that are more important than weather in predicting population growth in counties. All right, so this is the summary table of all of the models, and I am not going to go through this. I just want you to pay attention to the fact that there's one red circle. And so when we summarize all of our models, what we find is that the only counties that experience a statistically significant effect of any kind of hazard event on future population growth is in the high density growing counties. So think of those as the urban centers that are growing and have lots of, well, they probably have a lot going on in terms of their economic dynamism and other things. But it is only in those counties that hurricanes actually affect future population growth. So what do we find more specifically in terms of those the effects of hurricanes? What we find is that the effects of hurricanes on future population growth are not actually uniform. What we think about, and what David's talk sort of suggested, this environmental determinism model, is that, if you experience a bad hurricane, that's going to suppress population growth. But what we actually find is that that is true if you look at the green lines, where you see that in counties, that in these high growing counties or high density growing counties, if they experienced high losses associated with a hurricane event in the current year, that suppresses population growth over the next 3 years. If they experienced a larger number of hurricane events in the past decade, look at the blue lines, or the blue bars, that also suppresses population growth over the next 3 years. But this is the thing that's really interesting. Look at the orange bars. If a county experienced greater property damages over the previous decade, that actually is associated with higher than average population growth rates. So that's sort of surprising, right? But you can think about it as a way in which our disaster recovery policies really do a very good job of keeping people in place, particularly in places that are deemed worth investing in. So if this is a place that is economically dynamic And there's a lot of insurance dollars that go into recovering that place. That actually sort of increases the population growth of that particular place. All right, so this brings us to the question that we're all here to consider, which is, and it's something that some of the speakers this morning articulated. How can we nudge, fund, assist, and coordinate policies to replace these in situ disaster recovery and anticipatory land use policies in order to better cope with sea level rise and the more extreme weather events? This is kind of a perverse effect that we might be here to say, well, is this really what we want to be doing? And is this what our policies are meant to do? It is what they were meant to do in the past, but is it what we want them to continue to do in the future? All right. So this is just a summary of my main points. I'm not going to go through them again, but as I think this can be the beginning of an interesting conversation. We have these long-standing urbanization trends and complementary rural population loss trends that require different ways of addressing climate change adaptation. And we need to consider how our current policies, which privilege in situ recovery, might be tweaked to better address climate change. All right, so thank you for your attention, and I will now present our next speaker, although actually I have to, we have a little program change. In the last session, I got a message from Reid Bell, and he's not in the room because he was taking his daughter to the emergency room, and so he will not be giving his presentation, and I will not be substituting for him. So our next speaker is Tingyin, and Tingyin Xiao. She's from Princeton University, and she's also part of our Succinct group.
Sorry. Hi, everyone. Today I'm going to present our work on investigating climate impacts on South African internal migration through flow network analysis. This work is done with my advisor, Michael Oppenheimer, who is also with us today, and Xiao at the Stanford University, and Marina Mascherilo at FAO of United Nations. So you may ask, why should we care about South Africa? I guess many of us have come across the news about the Cape Town Day Zero water crisis last year. It was a big deal because Cape Town was nearly became the first major city in the world that ran out of water. It is a compound results of the 3 year of drought and the underestimation of the population growth for the water management, and plus the government failure. So under climate change, the climate risks such as the water scarcity is projected to be increased in South Africa, and compounded by the population growth, the exposure to drought was also predicted to be increased dramatically. On the other hand, the internal migration rate is very high in South Africa. It's about 12% in 2001 census and about 13.5% in 2011. And most of the migrants moved to urban areas, and this number is also growing. Previous research have indicated that South African internal migration is sensitive to the climate extremes such as drought and heat waves, and the different subgroups like different ethnicity, different gender, and different level of income of population also respond to the climate extremes unequally. And South Africa is still a very unequal country, even 25 years after the apartheid. This is an aerial photo of its biggest city, Johannesburg, and it's on the Time magazine cover in May 13, just last month. And unequal migration response to the climate risks is reshaping the communities all over the world, including the U.S. coastal regions. So studying the climate change impacts in South Africa is not only helpful for the local government and community to prepare for their future risks, but also meaningful and can provide some lessons to other unequal places in the world. And you may ask why we should need the network analysis. So accurately modeling migration flows is a very complicated task, and we started from solving a very important issue in the models. And we found that some of the widely used methods, such as gravity model, have an assumption that there is no dependencies between the flows, which is an unrealistic assumption for migration flows, and it can lead to biased estimation. There are some common migration patterns, including the bilateral migration or migration with high return rates, and the transit migration that people have a desired destination, but some of them will take a stop before they arrive at destination. And also the established corridors of the circular migration that people move in cycles. And these common migration patterns can correspond to the second order network dependencies of reciprocity and third order dependencies of transitivity and cyclicality. So using a network model, we can naturally account for these dependencies and solve the network autocorrelation issue. So this specific model we built for the migration modeling is a dynamic over dispersed Poisson version of Almond. I'm not going to tell the details of the model, but I will highlight some features of it. So because the inclusion of the additive term, we account for the senders and receivers heterogeneity in the model, which can account for the first order network autocorrelation. And the additive term, the multiplicative effect term consists of the latent factors UI and VJ. This term can describe the third order network dependencies. And also in the covariance of the error residual terms involves the correlation between the migration move to and forth between two destinations, which describes the second order network dependencies. So it can describe all the first to third order network dependencies, and but this is not the first network model we have applied, but it has some additional advantages because it's including a latent factor, the multiplicative term. It can control the variables that's even unobservable. For example, we can imagine some variables that can affect migration decisions, such as the relation to the land, or the tradition, or their lifestyle, which we cannot even quantify. It's hard to put in the model. But with this latent factor terms, we can control it in the model. And also because of this, with the trained model, with the historical data, we can also predict the future migration pattern. So this research we will focus on the water availability effects on the migration. So we use Princeton global forcing data sets to construct the several measurements to account for different types of water supplies and deficits. I will talk about that when we're presenting the results. The migration data and control variables are derived from the census and community survey data. So our definition of migration flows are the number of adults migrated between two districts during the past 5 years. So this is just a temporal configuration of the variables. Here we present some results from the models. Firstly, we calculated the positive maximum temperature and negative rainfall anomalies to represent the high temperature and low rainfall extremes effects. And the results here we want to introduce the notions, and the S stands for the standards. So the coefficients represents the push effects, which drive people away from a place. And R stands for receivers. The coefficient stands for the pull effects that attract people to places. So the results with all the population shows that extremely high temperature and low rainfall tend to push people away from a place, while the people are going to avoid places with extremely low rainfall. This is similar for the people going to the urban areas or move to the non-urban areas, but there is a major difference between them. So people moving to the urban areas tend to be attracted by the extremely high temperature, while people moving to the non-urban areas try to avoid them. We also calculate the soil moisture percentile, which can represents the agricultural drought, and we can see that anomalously low soil moisture percentile can push people away, but it doesn't have significant pull effects. This is similar to the two groups, even though the push effect is not significant here. But we also have to know that the two urban migration model has not as well, is not having a very good model performance here. We suspect that's because there is a lot of zeros here, and the model may not deal with the zero inflation problem very well. We also calculated a 12-month standardized precipitation index, which can represent the long-term water surplus and deficit. The negative as 12 months SPI can reflect the long-term meteorological drought. At this time scale, it can relate to the level of reservoir and stream flows. We divide the SPI to positive and negative values and insert them into the model with a dummy variable, and we can see that people, their extremely high rainfall anomaly tend to drive people away from a place, and people tend to avoid places with too many rainfall over a long time. And we can also see this effect is especially for the two urban migration. And across all the population, people don't like to move to places with extremely low precipitation. To examine the model performance, we compare the observed and fitted migration network, and we can see that the modeled results can capture the pattern of the observed. For example, the EKU, the red, sends most of the migrants to JHB Johannesburg and to TSH, and JHB sends back the most and send a lot to the TSH. This is also the same in the fitted pattern. This is just to show the model works. So all the coefficients shows that they are convergent, and the model captures the reciprocity and cyclicality well, but a little bit underestimated the transitivity. We also compare the model performance with the results from the gravity model. We match the model setting and using the same covariates, and we can see that this is the axis. X-axis is the observed migration flows, and the y-axis is the fitted, and the black line is the perfect fit line. So we can see that AMM results are more tightly distributed around the perfect fit line, while the gravity model results tend to be more dispersed and overestimating the smaller values, including the zeros. It is also reflected in the value of the R-squared. The AMM model results have much higher R-squared than the gravity model. In summary, we found that the more extreme high temperature has significant push effects in migration, while less extreme low rainfall has consistent pull effects, using either the negative precipitation anomaly or SPI. And the migration responds differently to different types of droughts. The less severe negative rainfall anomaly or long-term meteorological drought has pull effects on migration, and the agricultural drought has push effect on migration. And climate variabilities have different pull effects on the two urban and two non-urban flows. Urban-oriented migrants tend to be attracted by warmer and less rainy locations, and it may be the behavior of the sun-seeking. We don't know yet. But non-urban oriented migrants tend to avoid moving to places with more extreme heat. These are consistent in size and significance with the previous studies that only involves the push effects. The model we used have a lot of advantages. So it allows network autocorrelation, it controls unknown factors, it can improve the performance, and it can predict the future migration under climate change based on limited information. But we also have some technical issues to solve, like the zero inflation or rank selection. In this study, we used 8 pairs of latent factors, but that's a whole research topic on how to choose the ranks, and there are different series. We're not going into it. So this is the end of my talk. I have a lot of supplementary materials that I'm not going through, and I want to thank Peter Hoff, the author of AMM, for discussion, and Chris Strauss for introducing me to the methods. And I want to thank Michael Oppenheimer Research Group at Princeton and HU audience last year to our poster presentation. And thank you for listening to my talk. Thank you. Sorry, I forgot the question.
Your sun-seeking effect, do you know anything about air conditioning? I mean, I think about adaptation, the adaptation possibilities in urban areas are different than they are in rural areas, particularly middle and low-income countries. So poor areas tend not to have a lot of air conditioning, but rural areas tend to not have air conditioning in such settings. But in cities, even in poor countries or middle-income countries, there's often I'm sure air conditioning is not ubiquitous in South Africa, but I'm sure there is some. Do you have data on that, or any way of? It could be that it's not that they're attracted to warmer places. It's simply that the warmer place is mitigated by having adapted.
Yeah. Yeah, we don't have the data. We should look into it, and I think it's a very great suggestion. And I think this should be reflecting that because to the to non-urban migrations try to avoid this high temperature anomaly. It may be because they don't have this mitigation strategies, but that cannot explain why people. How can I say that? So it means that if there is no mitigations, should not people naturally should not seek for the warmer, too warmer conditions, but the population moving into the sunnier places, they also need to consider the temperature being too extreme. But the urban area, because they have this mitigation strategies, so they don't have to worry about that. They just need to.
Yeah, I mean, you might be able to get some data from local. The South African census actually has kind of a wealth of information on household attributes, and it might include whether or not there's AC.
Oh, okay.
Aggregate those data. And similarly on the, municipal water supplies, and sometimes if you're not agriculture dependent, right, it doesn't matter. It may matter less if it's not so rainy because you may have a policy strategy to get your water from, Botswana, or someplace far off. And
Yeah.
so you might, and there's also a database on where the cities get their water that you might, including in this, just to help understand these push and pull factors as they are mediated by other, adaptations to water stress, heat stress.
Yeah. Thank you for the suggestion.
So, I mean, these climate-related influences on migration, but how strong are they compared to migration decisions based on, say, availability of jobs or prices of housing, the things that you normally think about for why people migrate?
Yeah, so because our focus is on the climate variables, so we put other variables as the control variable and not showing here, but we put in the unemployment population ratio and education level and race and population. I think it's hard to compare the magnitude too because they are all in different magnitude, the observation data. But if we maybe we should look at the scaled variables and put them onto the same scale and to compare the magnitude of the coefficients. Yeah, but those variables are all in the model. Yeah.
So one is to look at the actual composition of migration flows, who goes to urban settings and who's not going to urban settings. And the other is that the factors that are pushing people out of a place could be completely different than the factors that are pulling people into, so that the decisions to leave are not exactly the same as the decision where to go. I think that your model could, very easily to handle those.
Yes, actually, this is a great question. So this the model is very flexible. So we can put in the what we presented here, like the senders and receivers nodal effects here. But we can also put in the dyadic effects, which can include the interaction between the two destinations. And we have looked at some of them, but it seems like, for example, the SPI, the positive SPI, we think, the positive temperature anomalies. So we thought that if the push and pull is in the same sign, then if I put in the interaction term in it, if the sign is positive, then it means that people move from the high temperature to the high temperature, then doesn't make many sense. But when you put both of the terms into it, and it's not significant. I think that means that people pushed by the effect are not the same as the attracted. So it's exactly what you mentioned. Yeah.
All right, thank you. So our next and final presenter is Deborah Balk.
Thank you, Beth. Yes, so for a change of pace, I'm not going to talk, unfortunately. If you're here to hear a lot about migration, I won't be able to speak so much about it. So unfortunately, I'll talk about why I can't. But I'm talking about the sister issue of urban change altogether, migration and urbanization. For the better part of half a century, we're always mentioned in the same sentence, at least in demographic circles. In the last decade, we've made a lot of progress. So 10 years ago, in 2000, a little more than that, 12 years ago, in 2007, we published a paper where we were, for the very first time, we estimated globally the population living in low elevation coastal zones. We created a low elevation coastal zone. We looked at urban population in the zone. We used new data sets to do that. It was the first time this was ever done. It was then put into the IPCC AR4. It was done with that in mind so that the human settlements at risk of seaward hazards could be identified in that report. At that time, we found that 1 in 10 persons lives in the low elevation coastal zone, and there you see a pie chart of how they're distributed across the globe, and it's really obvious that there are lots and lots of individuals in Asia, because there are a lot of the population of the world is in Asia, and as well, a lot of the Asian population lives in low elevation coastal zones. We additionally found that most countries with any land area in the LECZ, I'll use that acronym from now on, have their largest city in it. Small island states, which we've heard a lot about today from different presenters, as well as deltaic countries and their cities are at much higher risk. And so we knew going in that the small island states would have large proportions of their populations at risk. What we didn't know is how these deltaic countries would also appear to be to have huge risks as well. And that was sort of an important thing to quantify. Similarly, and importantly, we learned that 1 in 8 urban person lives in the LECZ. So the LECZ is disproportionately urban, and that's important. City dwellers in Africa and Asia, in fact, are disproportionately at risk. So you see in this graph, you see that 7% of Africans and 13% of Asian total population at risk, but 12% of African urban population and 18% of Asian urban population is at risk. That's what that is showing us. And this is important not because the disproportionate, if you look at all the other continents there, including the small island states, they're pretty balanced between their total population and their urban populations, which means that their urban and rural populations are at relatively equal risk. But the reason it's so relevant that Africa and Asia are disproportionately at risk is that most of the future population growth, total population growth of the world, will happen in the cities and towns of Asia, Africa, and Latin America. And so it's really important to understand that they're already starting off with disproportionate risk. Or vulnerabilities. So this work comes about from a fairly simple method, but it's one which is interdisciplinary in nature, and so and it depends on and it really depends on the quality of data. It combines demographic and satellite data. This is just a sort of a very simple rendering. You start with super small, to the extent that you have small polygons for census data. This is what census blocks would look like for the US. This happens to be communes for Vietnam, so those are administrative boundaries. And we know something about the population. Usually, all we know is population counts, which is why I can say very little about other characteristics like poverty or like migration status. Those characteristics tend to be collected at coarser units of geography like states. And if you're states are usually too big to do a very good or at least very precise estimate of populations at risk in a narrow band of coastal zones. I'm about to show you a wide band. These are urban areas, and these are urban areas as detected 12 years ago. And then this is the low elevation coastal zone as we identified also 12 years ago based on SRTM, coarse SRTM at that time. So the population data is measured in irregular polygons, and The underlying spatial unit resolution for those polygons varies by country and year, and in fact Vietnam, which we're looking at here, this was the 1999 census of Vietnam. They publicly released census for Vietnam in 2009, 10 years later, is not this nice, finely resolved commune data, but it's province data. So even within countries, sometimes you have a coarsening. The same happened in South Africa. South Africa had very fine geography that they made publicly available. The next census, they released a coarser geography. So it makes for comparisons over time sometimes tricky. We transform these to a grid, but your grid is only as good as your underlying data. And the grid allows for the then doing the summary statistics of relevance. The model data, we can use model data, which are, they present an alternative, so you can use some refinements. If time allows, I can talk about the various population models. But models have their limitations too. They're not perfect, and they also make assumptions. And to date, as I mentioned earlier, we only have population counts and population density in these population grids. We have age distribution too in the most recent round, but we don't have other characteristics of interest. So what's new? Why have we revisited this? Well, there have been a lot of improvements to the LECZ measurement. Now it allows us to distinguish at least between two zones. Oh, I'm reminding, let me just point out this is global work. So at this point, to anybody who works with LiDAR data or other DEMs might know that for a particular location, you can get better SRT, you can get better DEM, digital elevation model data, and create your own low elevation coastal zone for that location. But at a global scale, there have been a bunch of studies recently that say don't go below 10 meters. So when we first did this, everybody was very critical. Oh, how can, sea level's not going to rise 10 meters? And then we had a bunch of storms where all the storms were reaching 5 meters in height and so forth. So now with improved data, we at least have been able to distinguish two zones up to 5 meters and up to between 5 and 10 meters contiguous to coast. We also have new measurements of urbanization, and this is important because the earlier version we had a single time point circa year 2000, and as we know, urbanization has changed a lot and continues to change a lot, and the future population growth of the world will take place in cities and towns of the world. So measuring that urbanization and doing it in a spatial construct is really important. So these are spatial measures of urbanization that are coupled with population, and allows for distinguishing urban areas along a continuum, not just splitting the world into urban and rural as we did for the last 75 years. And furthermore, we can also characterize the built-up density of these different types of urban, semi-urban, and rural locations. And finally, in this revision of the work, we're looking at change over time from 1990 through 2015. Also important if we ever wanted to forecast anything, go forward, it's important to see what's happened in the past. And also a pressing question has been, has this low elevation coastal zone been growing more quickly or slowly than other areas, which is a question we couldn't answer the first time. So the use of temporally varying measures of population in urban areas were previously unavailable. So at least for urbanization and population, we can do this. The low elevation coastal zone itself is still only for year 2000, but it's also an open question on what the desired time steps would be for a global study. Sure, for any location, Hurricane Sandy came, transformed the coastline of parts of, the North New York area, Hurricane, Maria transformed parts of the Caribbean and so on. Any storm will have an impact in a particular location, but for global studies, you could argue that, you don't need annual data, you might not need decadal data, and maybe every, maybe 20 years. This is an open question. We'd be really happy to hear what the geospatial and the geophysical community thinks about what the right measure, the temporal measure would be on this. But in any event, there is no time varying measure currently available anyway, but open question as to what would be desirable. So this is how we measure the low elevation coastal zone. This is greater Bangkok area in Thailand. This is the 5 meter zone. This is what happens when you go up to 10 meters. This is based on the SRTM 90 data. It's reconciled with coastlines, which is important because you don't want to actually miss something because of coastlines come from administrative data. Administrative data are not necessarily as precise as you might imagine they would be. And this is the only globally available data that was available for processing. We're actually doing some new processing now with two newer data sets. And as I mentioned just a minute or so ago, recent studies caution still against using SRTM data to consistently measure LECZs below at like single meter increments, 1 meter, 2 meter, 3 meters. So we do it 5 to 10 because there's a tension between what the policy and planning and community wants and maybe what the science can support, but we do it suggestively, and then we treat our results here as suggestive but not definitive. And we also are processing one of the other newer data, the Merit DEM, which is still based on SRTM, for another estimate, and that's ongoing, and some other newer data sets may be processed in the near future as well. So that's how we measured low elevation coastal zone. This is how we measure urbanization. This data set comes from the out of the European Commission and the Joint Research Center. It's time probably will not allow, but it's largely based on a combination of population and the Landsat archive to look at to come up with criteria for measuring what are called urban centers. Those are things that you would recognize easily as cities. I could just call them cities, but they're called. I'm just going to go with the language that comes with the database. Those are places that have population densities greater than 1,500 persons per square kilometer, or populations of 50,000 or more. And then those are in contrast to quasi-urban clusters, which is they call them urban clusters. But I have, from some of the validation work that I've been doing in 3 countries, the US, Mexico, and India, I'm not really sure that they're picking up. They may be overestimating urban areas in some places, and particularly that's my concern. So I don't want to call them, I don't know how urban they truly are. But what I do know is they probably are something in between a village, and some kind of city and town. And in fact, this database, if you're interested in it, is publicly available. I encourage people, it's available. You can Google SMOD degree of urbanization grid from JRC, or see the paper authored by Florzik as to take a look at these data. And I encourage the more people to look at them, the better, because they'll make changes in it, and that's the way this data, the first database that we used was GRUMP, which is a database that I was involved in developing, and this is a much improved version of something like that, but it's not great. It's got a lot of, but as a community we can make changes. And then, so these quasi-urban clusters are populations that have population densities of 300 persons per square kilometer and populations of 5,000 or more. So you might be thinking, oh, well, most Indian villages will fit into that. And if that's, and so therefore it might overcount Indian villages. It's not exclusively just the density criteria. There also has to be a built-up criteria. And then this is what it looks overlaid with the 10 meter low elevation, 5 and 10 meter low elevation zone. So we do this for 90, 2000, and 2015. It's not a continuous time series. It's a time series in those stamps. There's an earlier time period to 1975, which I omit here. And the method for this urbanization measure is it reallocates the gridded population of the world input data to the global human settlement layer built up data based on contiguity and population rules. And then finally, the population data looks something like this. And then you overlay them as well. And this is actually a modeled population. It uses the gridded population of the world data set, version 4, inputs reallocated to the built-up area on the global human settlement layer. We use this because it's more consistent with the degree of urbanization data than just using GPW, for example, or using one of the other modeled population data products. If anybody's interested, happy to tell you more. This has some limitations because where GPW or census inputs are particularly coarse, there will be a tendency to reallocate people, to concentrate them where there are built-up areas, and then built-up detection is good but imperfect, more so in the earlier years. Okay, so what is urban? Measurement really matters. Confirming our original findings, the new estimate places about 11% of the global population in the LECZ, but it places more urban residents in the LECZ. 14% of the population of urban centers and nearly another 10% of persons living in quasi-urban clusters. And so you might come up with roughly 25% of the urban population of the world rather than 1 in, and so that would be 1 in 4 rather than 1 in 8 from our earlier estimates. So it really matters how you're measuring urbanization. If these quasi-urban centers are not truly urban, then you may have, then you may be misestimating things. So, and you can see here that the population of the quasi-urban clusters in the rural areas is pretty evenly split between those living at low elevation and higher elevations within this zone. But you see within the most urban, the places that are obviously urban, obviously cities, those places people tend to live in the higher portion, in the between 5 and 10 meters. So that's useful. We can look at the distribution of population and land area. We find that 61% of the population of the LECZ itself lives in these urban centers as compared to 47% beyond the LECZ. So that's why the big red portion of the pie is larger on the within the LECZ side than on the other side, and slightly less than half of the those living are living in the 0 to 5 zone, not shown. And then we have 12% of the land in the LECZ is an urban cluster or urban center, one of these quasi-urban clusters, as compared to 2% of the land outside the LECZ. So that is just a gigantic difference. And these fractions, I'm showing you results here for only countries with land area in the LECZ, but if I look at all countries, there you go, the fractions are essentially unchanged. Just the pie switches gets a little smaller. And maybe important to note, and also worth critical review, is that these quasi-urban clusters are, in fact, they occupy much more land and have many more people than do urban centers everywhere, inside or outside the LECZ. So again, let's not just accept those uncritically. So we've then said, okay, and this we couldn't do previously, we said, what are the rate of growth in population in the LECZ? And so here we see that in urban centers experience the highest rates of growth, both inside and outside. Inside are the dark blue is the lowest, the lowest lying areas, up to 5 meters at highest risk. 5 to 10 is the lighter blue, and green is outside the LECZ. But the urban centers clearly, are clearly obviously very high growth rates, much lower and even lower there. But for quasi-urban centers and rural areas, the growth rate is greater outside of the LECZ, but the rate of growth is so much lower overall than the urban centers. And in all types of location, the growth is greater in the highest risk zone under 5 meters of note. And we can come back to this one when we want to talk about managed retreat. The annual growth rates, for the most part in the past 15 years, growth is slower than in the prior decade, and this is probably largely because we already have very large cities in these zones, so as you add people to them, the growth rate is just heaping onto very big numbers, so as opposed to small places having larger growth rates. So in addition to looking at growth rates, we can look at population density. In 1990, the LECZ was, we estimate that it's nearly 6 times more densely settled than land outside the LECZ, and with faster population growth rate in the LECZ in 2015, densities were almost 320 persons per square kilometer within it, and slightly more than 50 persons outside of it. The likely causes are simply the LECZ's disproportionate urban nature combined with the higher urban population growth. And in situ urbanization, change of rural areas and these quasi-urban areas to more urban areas. Like this is land use change as well as expansion. This is just places becoming the process of urbanization occurring in place as opposed to more people migrating into cities. But this process can also lower the overall densities because as you add more sparsely populated urban areas to your total urban areas, you should see the overall densities decline. So let's take a look at what's going on within these different city types and within urban centers. We see that the highest densities are found outside the LECZ, but those are very close to what you find in the 5 to 10 meter LECZ. Densities are a bit lower in the highest risk zone. It's risen from 1990 to 2015 in urban centers, and more so, more or less stable outside. In quasi-urban centers, we see that they are about 3 times less densely populated than urban centers. Here too, the areas at highest risk are the LECZ, are the less dense areas than the 5 to the. So the highest risk zone is the lowest, has the lowest densities, and the densities are largely stable. And here we do see slight declines. And again, that's probably because these areas are some of the most densely populated areas that were once classified as urban clusters are probably switching categories over time and becoming an urban center. And so they join what remains is the less dense places. And then finally, rural areas, obviously densities in rural areas are orders of magnitude lower. Like if you're watching the y-axis here, like it's really much lower than anywhere, but than even quasi-urban centers, but they're 3 times higher in the LECZ than outside of it, for example. So rural areas, and again, this might have something about managed retreat because you have a lot of rural dwellers within the LECZ, more densely populated rural areas in the LECZ than you find outside of it. Access to fishing, access to waterways, other sorts of amenities, or like ecological amenities. The last thing we asked that we couldn't ask previously is not just about population growth rate, but built-up area growth rate, which is something like impervious surface, but not exactly. It's literally building density as derived from this Landsat archive, from the global human settlement layer data. And we ask, is the LECZ like other areas? Well, we find that the 5 to 10 meter LECZ has the highest built-up levels, but only slightly more so than areas outside the LECZ. And urban centers are twice as built up as quasi-urban centers, which are more than twice as built up as villages. But the higher risk LECZ is less built up, especially in urban centers, and I would like to know whether this is actually evidence of historic urban adaptation of some sort, possibly, but the question we have yet to answer. And then we can similarly say, well, what's the growth rate of these places, just like we asked about population growth rate. So, and with similarly, the rate of growth of built-up areas in urban centers is highest in this low-lying area between year 2000 and between 1990 and 2000. And then again, rates of growth rate are lower in the more recent period across the urban continuum, and perhaps that's because once built, a place most likely stays built, and you don't see it's only and the built. This is not vertical building change; it's simply more. It's a horizontal measure of road. It's not even roads, but just buildings of any kind, of any height. So, in conclusion, the new and improved data product allows for refinements in understanding who's at risk of these C-word hazards. In addition to 14% of urban center dwellers in the LECZ, we find 10% of these quasi-urban cluster residents, whoever they are, these people who are neither clearly rural or no longer rural and not clearly urban. So much greater attention to the urban continuum, I would argue, is needed for us to figure out who these people are. Population growth rates are highest in the urban centers of the LECZ, and with higher rates of growth of population and built-up areas in the in the 0 to 5 zone of the higher risk zone. So we need to get a better grip on that zone and use better DEMs that allow us to estimate this with a lot of rigor and confidence. And then finally, the causes of urban growth in the LECZ remain unanswered. We don't know, is this land expansion of existing cities or the emergence of new urban places contributing to this growth? With these new data sets, we can actually start to answer that question. So that question we will look at. But the second question, like the role of migration versus natural increase, Why these places are growing, apart from the physical space that they occupy, remains an unanswered question. And except for work that's done on a country scale with really good survey data, is unlikely to become an answered question anytime soon, unfortunately. So, but answers to it would help in climate adaptation. So it would be nice to have those answers, but we have to punt on them for now. But better to understand at least what areas are growing, if not why, as a start. Thank you.
All right, well, thank you, Deborah. And so we have 15 minutes for Q&A, and I did want to say I got a text from Andrew, his daughter is okay. So we were prompted to sort of organize the Q&A a little bit around a couple of questions. One is, what's the take-home message of what we heard today? And I'm going to just sort of summarize what I heard, because I think it might be helpful for getting a conversation started. What I'm hearing from the 4 presentations that we heard today is that people are continuing to move towards cities and towards cities on the coast. And so there are more people moving toward, this is the opposite of managed retreat, right? But the other nuance that I heard that I think is really important that came out in Tingyin's talk was, in particular, is that people are moving away from dry places. And that also was, in the study of the United States, we're not seeing we know that the rural places are losing population. And that's an interesting compliment that we haven't heard a lot about in our discussion of managed retreat. But it gives, but since we have seen evidence of that in some of the talks today, it's worth considering, why are these two things happening and what do they have to do with each other? So I think that the other thing that we've maybe not heard explicitly, but that is part of the discussion when we talk about combining population and environment data, is that it's really hard. And I think Deborah really made that point. She's working extraordinarily hard to use the data that is available on population globally and land elevation and settlement patterns globally. And it's really difficult to wrangle all that data and get it to speak to each other.
And just to answer a bunch of descriptive questions.
Yeah, and you can describe what there is, but then moving into that explanation of why these patterns exist and how they're changing over time is super challenging. But we're making progress. So I think that's what I heard as the major takeaways from these presentations. I'd like to open up the conversation to hear what you all heard from as a major takeaway, and then particularly what it has to do with the larger conversation about managed retreat. Oh, sure. Do you want to sit up here in the front? We can take it, but I'd be happy to have this not so much a back and forth, but just have an open conversation. So, Richard?
Yeah, I'd like to back it up a little bit, because I think Deborah's question she posed at the end is very interesting. So, fundamentally, why are people, these cities on the coast, grow, wherever it is? I mean, it's examples there in Asia, but even in the United States, I mean, the cities were originally there because of transportation by sea and the fishing, the resource exploitation. That now very few people are employed in maritime industries. So, but still, Seattle, San Francisco, Los Angeles grow, right? But is that still in some way because of their port access, or is it just?
I think it's their history. What became port access transformed into economic or political, centers for employment and so forth. And they, these cities, cities mostly just don't disappear. So once you have Nigeria, parts of, coastal China are gigantic cities starting, along through urban agglomerations. So I think historic precedent is really, really important, and momentum, as a demographer, I feel compelled to tell you that momentum is like perhaps the one thing you can count on in your modeling of future population, and it seems to be true of urban population growth as well. Simply, and in fact, to most population growth in cities is not migration. It, to date, as far as we know, it's a hard to answer question, but it's still driven by natural increase, not by, that is first guess, rather than migration. Except, some countries that's not true for, but globally that is still true. So momentum is an important force in the growth of these places. And, so yes, because they were once maritime ports, is now why we have.
So Liverpool, I'm from Liverpool, which is the exception, right? It's now half the size.
Yeah, Liverpool is like the Detroit of England, for example. I mean,
well, it's a good comparison.
Yeah, no, some cities, it's not, there is some heterogeneity. Not all cities grow at the same rate. Like, smaller cities grow much more rapidly than large cities, for example. And there are some cities do decline, but for the most part, cities don't decline. And it hasn't gone away completely,
No.
It's just a smaller city.
Oh.
The related question then would be, what would make these Detroits of the world, more attractive inland cities to people to move to them? What kind of incentives, and what would also, how would those inland cities respond to the diverse nature of the populations that coming out of the coastal zones, from the areas coming to them? This is the question that was asked earlier. Presentation, manpower, but the college of most of that college is no exception.
Well, so one of the things, and so I'm going to kind of answer your question indirectly, but you talked about Matt Hauer, and I also work, Matt Hauer is part of this think group as well. And some of the data that he uses and that I use as well looks at migration networks in the United States and which places are connected through flows, whether they're in migration or out migration flows, and this sort of directionality. It's very much like the work that you're doing. And I think that network approach can be useful for thinking about what places are connected and how those connections are social networks that might connect a coastal city to an inland city. And that would be indicative. For example, in my research, we looked at the migration network of New Orleans before and after Hurricane Katrina, and we said, are the places that were connected to New Orleans through out-migration flows before Katrina the same places that then in the future, in the years after Katrina, sent people back to New Orleans? In other words, that would be some evidence that there was sort of a displacement to familiar places and then a return migration to New Orleans from those places that represents that sort of exchange. And we found that indeed there was that kind of almost, I think of it as a sponge effect, where you have the sponge, you press it down in one place, the water gets redistributed to the other cells in the sponge, but then when you relieve the pressure, they move back to that place. That same sort of idea could be used to think about how sea level rise or policies might take advantage of a network, a migration network, to redistribute people. And I think one of the things that we've discussed here is that policies can be powerful, and maybe they're what we need to focus on before, rather than waiting for some crisis to occur. And so the question is, like, how do you direct those policies and coordinate places? I think that's super challenging, the governance question. How do you create these coordinated networks of places that would together confront displacement from sea level rise or coastal events?
I want to add to this comment, which is that you have policies as well as incentives which can be policy driven in some places. I mean, if you Alex, you posed the question, can we make Detroit more attractive or Liverpool? And did Jesse last week talk about the loop? Yeah, he talked about the loop, right? We should all be moving to the loop. And, you know, yeah, I'm sure the loop is actually a really nice place. But okay, some city in Minnesota, Minneapolis is one. I like Minneapolis in the summer, and we mind in the winter. You can stand around. But the thing is that as long as there, you know, one issue is, you know, it's not really clear. I think it's important to recognize. I'm not sure. The question is, how can we make these other places more attractive, per se? It may be the wrong way of framing the question. It seems to me, when we first published this study, it was Lester Brown did these results and said there are 634 million climate migrants. There will be 634 climate migrants, and there was no evidence to suggest. We never said these people were climate migrants. I see no reason. I think what's most likely to happen is there may be some, very local reallocation. So the question, like the jobs are still, for the most part, I mean, sure, let's make the Loop and Liverpool and Detroit and cities that have infrastructure and can accommodate, if they can accommodate more people. I'm not really sure Detroit is a city that can accommodate more people. It has it's a city that's got a lot of problems, doesn't have fully financed now. I mean, it's not a very healthy, it's a city with, that's trying to revive itself internally. I'm not sure adding more people to it will make that an easier revival. But we can ask the question, we should be asking questions in these cities that are at risk. How do you stay in the same labor market but not be flooded in the next major storm? And those questions are some of the questions that are being asked here, right? But I think that is the most likely form of migration that's going to happen. And that may not even register as migration. It's going to register as an internal migration, as a residential mobility move of some sort. And so a lot of this will happen within this statistical record keeping system in a kind of invisible way. And so I think that's worth thinking about how to, think about that problem.
All right, well, thank you. I think you got the last word. So thanks, everybody.